Okay, now we are complete. Welcome to today's webinar, Model and Design Timber Structures in RFEM 6 and RSTAB 9. My name is Andreas Hörold. I'm responsible for marketing and public relations in the Dlubal Software company. For instance, the Dlubal website, German and English webinars, customer projects, etc. I will be the moderator today.
Yeah, hello also from my side. My name is Bastian Kuhn. I'm responsible for customer support, trying to help you with any kind of questions you have related to our software, and I'm also developing timber design add-ons in our software.
Okay, then it's my part. My name is Gerhard Rehm. I'm also responsible for the customer support, and yeah, I participate for the development for our related timber stuff in the program together with Bastian.
Okay, thank you. Then we can close our webcams that the attendees can see the full screen. Okay. To the organization, you can ask questions during the webinar via the control panel on the right side of your screen. You can show or hide it with that arrow here, and then you can ask short questions here. If you don't get an answer during the webinar because there are too many, you will get an email after the webinar. The other way is to watch the entire webinar and then email your questions to info@dlubal.com. To the agenda today, first point is timber structure modeling in RFEM 6. It will be done by Bastian. Then he goes to the second part, load input combinatorics. Then the timber design according to Eurocode 5. And he will document all in the printout report. Then he will hand over the screen to Gerhard, and he shows two examples with detailed design, for example, modal analysis. Then I hand over the screen to Bastian, just a moment. Okay, Bastian, it's your turn.
Okay, just hold on. I have to choose the right monitor. Okay, I hope you can see the screen. Yes, that's there. Yeah, welcome once again from my side. I assume that you know a little bit about our software, otherwise you probably would not join this webinar today. But anyway, we have now introduced the new RFEM 6, and because of this, I will also lose a few words to the basic design or input data that you need to define in the RFEM 6. However, this is not intended, the intention of this webinar is not to give you full training, so it's either not possible that you model directly the things that I'm modeling. I think it's not possible. And we are also not losing very, very detailed information about basic data. For this, we have other webinars where probably Andreas Hörold will give you an introduction later on that already been held. All right, so when you start in our new software RFEM 6, the program, and we just give our model a name, we will call it webinar, maybe also the date of today, that's 2021. There, what's probably the first difference, if you know the RFEM 5 software, we have here the type of models, and there's a 3D model, what you probably all know and what we are dealing with today. But we also have increased the options for the 2D model, and there is this last one here for 2D, XZ, 3D, and also for XY, which means that you can model your structure 2D but design it in 3D. That is, I think, a good point for timber design, especially for timber design, because it's quite often used. That's what we know from our customers. But of course, today we will start with the 3D. The other points I refer to the already been held webinars for RFEM 6 where this is explained. One of the other big changes compared to RFEM 5 is that we have included all the design add-ons directly into the software, and therefore you have to choose what kind of elements you want to design from the start. For my structure, what I will define here today is enough to have one way the combination wizard and the classification and the load wizard, and also the timber design. All the other parts are not part of this webinar today. I think Gerhard will show you also a little bit about structure stability, but I will use the simplified method, which is included into the timber design as well. Okay, now that I've chosen this add-on, I can directly go to standards and choose the Eurocode 5 here with the timber add-on. When you choose the standard group timber here, this button here is active and you can edit the national annexes. For timber, maybe not the only, but the important point what you should change here is, or where you should take a look on, is the deformation coefficient with which you are regarding creep into your structure for the serviceability limit design situation. Well, it's divided into service class 1, 2, and 3. For service class 2, it would be 0.8, 3, it would be 2. As we are designing everything today in service class 1, we can choose 0.6 as a factor. To the other factors, I will not lose too many words as they are not important. I will do the design according the German annex for the Eurocode, but of course you have all the annexes for Eurocode listed here, and you can edit them however you want to do it. One point I forgot, of course you do not only have to design according the Eurocode, it's also possible according the American standard, Canadian standard, Brazil, India, Switzerland, and so on. There are quite a lot of standards available. For the load wizard, I will also choose the same national annex for Germany and for the timber design as well. Okay, then this input is already ready, and then on the 5th register in settings and options, that's quite an interesting new feature as well, what we call member representative. When you activate this here, we have another register open up, and there you can see that you can consider member properties. I will explain later on directly in the software what this means for the practice in the design. Just to give you rough estimation about this now, you can unify several members into one representative, and the advantage is that you do not have to give design parameters to every member, but you just have to give it to the representative. So that's a very short explanation to this. Then the last register in the basics, what I want to show you is the model parameter, where you can select the location where you want to build your structure. So maybe we will give the explanation, the location of our office here in Leipzig. It's Grimmarsche Straße, and press OK. And now we have the location, and one of the great advantages of this is that you do not have to take care about snow load, wind load, and earthquake design anymore, because all the relevant informations that are given by the location are already inside the software via this. So that's quite a handy tool to have. So now we are in the graphic screen of the structure. If you know RFEM 5, you will probably know or you kind of get a feeling that how this works. Right clicks here, there's the data navigator. So we've changed a lot of things, but the view or the work with it, I hope is known to users who are working with our software for a longer time. Now we want to design a hall, and therefore we define a new member. We have here the member types. At first we will start with a beam member type, and as we want to define a column, we will give the end of it a hinge. Here, a moment hinge at the end. Just simple this. And now there's the second register section with the distribution type that has been increased quite a lot with the options that you have there. So you can like either design a tapered member, the alignment you can choose. That's also it's much more user friendly than how you did it in the RFEM 5, because the alignment and the eccentricity that is coming from it is calculated automatically, and there are also several design types that you can choose here. Anyway, nevertheless, today we are concentrating, or in this part of the webinar today, we are concentrating on the uniform distribution type. And we want to define the section. You see there's already predefined a section of 14 by 28 centimeters, but that is not what we want here. So we go to the library. The library is divided into the steel sections on the left side, once the standardized and the parametric sections, and on the right side you see all the sections relevant for concrete or for massive design and for timber design. We are able to design all the sections that you have here under parametric massive 1 in our add-on timber design. Here, and you see that there's a whole bunch of sections possible, but today we will also concentrate on the massive rectangle sections. It's always opening on the other screen, and we have now here the list of sections, and I want to actually have a section 14 by 14 centimeter. I want to have it isotropic linear elastic from the material model, and if I click onto the library here, I get directly to the material library. If you know or if you are working already with the RFEM 5 software, you probably knew that the material database is maybe a little bit flooded or overloaded in RFEM 5, and we really tried to clean that here. So if you go to Europe, of course there are all the other countries possible there as well. Solid timber, you see that it's quite a cleaned up view, and you have not so many materials available anymore, as they are, from our opinion and also from the customer's opinion, are way too much in RFEM 5, and now it's much easier to get it. But of course you can also use the search function here on the bottom. I'm using a C24 standard material for timber design, 14 by 14. Sorry, I was a little bit too quick, I think, because when you choose the C24 inside here, you have here a register with the material values, and here in timber design you have all the relevant data that you would need, the material properties, and also the design parameters for ultimate limit state, fire design, and so on. And you can modify them here as well. So if you want to change the burning rate for what reason ever, it's possible to do it in here. Okay, yeah, this is the section. The other points are probably mentioned by Gerhard later on. Okay, and this was the wrong section. I wanted to have the 14 by 14 centimeters. Okay, these are the first three registers, main, section, and hinges, what I showed you now. And there are also 3 more registers: design types and design configuration. That is one of the big changes in RFEM 6, that now you are defining all the design parameters according to member. It has the great advantage that you can change the design parameters for different member, e.g. a column may have another design parameter than a girder or anything else. But I want to model my structure first, and then I will show you these dialogues and also explain you what it does, and also explain the member representatives with this. So this is now just for your information, and I will model the structure. So the first column will start as its origin and should have a length of 4 meters. You see that here, if you open this drop-down box here, that there's already assigned the representative, and it has also this little box which yeah, it shows me that this is a representative. Then I will give it a support. Oh, that's a little bit too small. If you want to increase the size a little bit, you can do it here. Oh, that's still not that good, I think. Okay, but yeah, maybe we also not overdo it. Okay, that is this, and then we will copy that in 40 meters to the right side, created one copy in X direction, 14 meters. Okay, and there it is. And then we will have one of the other girders, and this should have another section here. Actually, I want to have this section suits me good. It's 14 by 28 centimeters, and also GL28C is the right material for me. Define it here, and then divide this member by 1 node. Okay, so and we see now that you have 2 member representatives here, and that the column and the girder is already divided by that. So we want to have a roof angle of 13 degrees. That gives me some height kind of this, and here probably one edge I also want to have a hinge, and therefore I'm defining it there as well. So now we need the bottom girder of the little truss that we are designing, and that will also be, in this case, I'm using a truss type, because all the other elements that I have should actually not be loaded by bending, so I can use the truss type in here. And as a section, I have to define a new one, and this will be, let me look, 14 centimeters, whoops, 14 centimeters by 26 centimeters. And of course, in this size, I'm also using GL28C. Yeah, okay, the other points I will mention later on, and define this here. So, and now I have the third representative in here. This members here, I'm now also dividing by intermediate nodes, but there is a good new feature that we have here. You, on the bottom here under options, you have the option to create on member nodes without dividing the member. So, and if I choose now 2 intermediate nodes, press OK, you see the beam still has its original length of 14 meters, but I have here intermediate nodes that are not dividing my structure. And this is also one of the advantages in RFEM 6 compared to RFEM 5, that we do not divide, or you do not have to divide the members so often, and then the options what we have with set of members are maybe not really needed so often. I mean, they are still probably needed for serviceability, limit design, and so on, but not that often as we had it in RFEM 5. Okay, now I will define the intermediate sections or members. They can also be a truss type. Actually, now everything I'm doing is defining truss types. Define a new section here, and that should be 120 by 120. And then of course I can use the C24. I choose this material here, say okay, 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 and yeah, define it here one way, this, tuck. And now it's probably very obvious what the representative does, because now it's clear that left and right side are similar, and you see that they are unified here under this representative. Okay, one more time, and now it should be ready. Yes, that works. And this structure I can now maybe load for the self-weight and the roof setup in the first load case, because it's quite simple here. The first load case is already assigned, and so I choose here 2 kilonewton per meter. Load direction ZL is fine to me. Say here or here, okay. And now I have it there. And now the last thing I need to do for my hull is to copy this again, but now in Y direction for not for four times, but for 5 meters in Y direction, and here 4 times. And now if you activate under numbering and options the link steps, you can also directly connect all the related parts to each other. Therefore, we will also define another member. This can also be a truss type, and the section probably it's enough to do 12 by 12, but yeah, maybe just to be sure we take 14 by 14. It's okay. 14 by 14, C24 can stay, so that's okay. And okay again. And now we have it. Also the load is here. Now the beams on the bottom, they probably make not so much sense, and therefore I'm switching off the member representative, and now I can just simply delete the one at the bottom. Okay, okay. So, and if I go into the other direction, also the one right here, I will also delete. I can delete the lines actually, because this deletes the members as well. Lines and delete. All right, perfect. So that looks quite good to me. That's a truss. Okay, now I know I forgot one thing. The load here on the side should be the half of the one that we have in the middle of the field. So that is easy, because 2 divided by 2 is 1. And now we have it right here, and this hole is now still kinematic, pretty obvious to everybody. And now we need to define there also stiffening elements. I choose to define my stiffening elements in near the middle of the structure, because it makes the most sense to me. Once again, divide the member by 1 node and without dividing the member, and define the section there. And I'm once again choosing the truss and the section 14 by 14. Okay, oops, here as well, tuck, and here. So now the walls are stiffened out into the Y direction. I will do the same for the roof. So come on, this and this and this and this. Oh, that was wrong. I saw it already. Okay, I'll get out of the dialog and grab it here and move it to this node. Okay, maybe switch on the representatives just to see it again. And for me, it's a good help to have it. This, I will just do one side of the structure. Hold on, and also, oops, that was, come on, too quick. I also will stiffen out the front of it. Therefore, I will just delete this here, because I want to have a complete fixed wall there inside. And so now we cannot have the representative. That makes no sense. Yeah. So we do it this way. Copy it here. Look. So, and then we have it. And if we fix that to the bottom, it's there. And here, once again, the last cross section. 14. Okay. So. And for my roof, I will also give some stiffening elements right here, here, and here. Okay, quite a lot of drag and drop or modeling, but yeah, I promise that's it. Okay, so, and then we copy or we mirror it to the other side. So this, and now we mirror it, we create a copy, and we use the YZ plane and copy it directly at the ridge. All right. So now it's there. We can make a little test and save it directly in this folder before we make the little test, how it's working, before we start our loading for snow and wind. That's what's missing already, but that looks quite good. And so we have a load, and 9.7 millimeter deformation looks also quite reasonable. Okay, now one of the other great features that we have in RFEM 6 compared to RFEM 5 is the so-called load or surface type load transfer. So when you define a new surface here, and then press OK and define it here, I will explain the register right away. Yeah, that's okay. And even it does delete the result, it's still, you do not have a worry. This surface type only distributes loads. It does nothing else. It gives no stiffness to your structure or anything else. So it's only distributing the load into its plane area to the edges of it. That's what I want to achieve in here. So now I want to explain the register. So if you double click onto the surface again and go to load transfer, you have here also an option to say remove influence from parallel to members. And in this case, I only want to distribute the load similar as what I did with the self weight to the main member or the main beam here. So then we will use this one and this one. And this one, actually, I was probably on the other side, I think. But I think it should not matter. But just to be sure, I will use them again. Okay. And yeah, I was on the other side. Okay, but then I can do it here similar and select it here, here, and here. Press OK, and now I have defined the distribution, and I want to show you in the snow load generator what kind of effect this has. I already said that probably the work, if you know RFEM 5, is quite similar to RFEM 6, but one thing that has been increased by its options enormously is the columns here on the bottom. And that's what I want to show you here. The load wizard is now also integrated into the column. And if I go to snow load in here and double click there, I can choose the dual pitch roof, and then choose the nodes of the roof. And you can choose the roof side. The parameters you can control. You see it's already assigned all the relevant parameters of the height, where my building is located, the load zone, and so on. The load cases I need to define for this webinar today. I just gonna show you the load case full snow load and not the points with the half snow load on the left and the half snow load on the right side. I think that is enough. And also for this kind of structure that we are defining in here, it's probably, well, I think any engineer who's designing a structure with a dual pitch roof will mainly use this, or it's mostly the design giving roof. Okay, I will define 3 load cases more, the one for the snow load that we are using right now, and 2 more for the wind loads, because we want to define them as well. All right, so now it's choosing the load case 2, and if we select OK and jump to the load case 2, we see the envelope of the load that's generated in here. And if we go to surfaces and display load separately, you can see that because of my load distribution surface that I have defined, the load is correctly transferred to the main girders of the structure. Okay, okay, one more time we do the same for the wind load. There we will just choose the dual pitch roof with the roof corners. Here, select the points once again. No, there and there. I would just define 2 directions. So I will define 0 degree and 90 degree. Just I think, I hope that's right. Yeah, I think so. Here I have to define my structure height, though that's 5.8 meters. All the other parameters are overtaken from the first input. For the webinar, I will just use the uplifting wind loads and not the wind pressure loads. All right. So, and now when we look at this, here at the load case 3, so that looks quite good, I think. And in the load case 4 as well, maybe we say also please display that separately just to check it, but it looks reasonable to me. All right, and so, and here you can see the wind load zones as well. Okay, so structure is done, and now we will concentrate on the modeling, or on the load combination. Sorry, that was a little bit too quick. Here you can define what kind of load cases and combinations you want to assign and calculate. I have the combination wizard activated in case you want to make your own definitions of load combinations. You just have to deactivate that. For our purposes here, we will use it. The design situation we want to verify is ultimate limit state and 3 types for serviceability limit state. And I also want to do fire resistance verification. For this, I will define an accidental combination. Here in the info box, you can always see what the software is doing with it. So you see here the creeping factor that I introduced in the start in the basic data, where it is located and where it is used in the software. I already did check if a design according second order theory is necessary. It is not, and therefore I can say the load combination can be generated geometrically linear. Okay, so now that's done, but I forgot one thing, or not forgot, but I mentioned it, that we need to define the design parameters before we are designing the structure. And now we have the representatives here. So, and the first representative we can activate is for the top girder. So that's probably the representative we need to take the most look for regarding stability problematics. And if you go here to design types, effective lengths, you can one time consider the effective lengths for buckling and for lateral torsional buckling. We are also able to verify such elements via an eigenvalue method, but this is going to be shown by Gerhard just in a few minutes when I finish this my side of the presentation. And therefore I will just concentrate on buckling and lateral torsional buckling with the equivalent member method. That's what I'm doing here. And I'm actually switching to absolute values because I know, the hull has a width of 14 meters and the half of it is 7 meters. So I say for the strong axis, I can use this one, and for buckling in the weak axis and buckling or lateral torsional buckling, I can choose the distances of my stiffening elements that I defined, and there are in a value of 2.58 meters. Say okay, service class is 1, that's okay. Local section reductions in case you have any kind of plumber or electricity that's kind of cutting your structure, you can also define it in here and decrease the strength of it. A shear panel and a rotational restraint are more or less mainly for the eigenvalue method that is going to be shown to you by Gerhard. For the top girder, I want to do an ultimate configuration for sure, because that's what I want to do for all elements. In this, I want to perform the stability design check. That's also for sure. In case it is a column and I'm in moisture class 2 or 3, I also should have reduced the stiffness, but this is not relevant now for us. And the shear design is, I think, also not relevant in this case. Okay, serviceability for the top girder is not relevant because when I'm verifying the deformation in the bottom girder, it's more than enough, so I can switch that off. And fire resistance as well. I will get to that point when I take a look at the other elements. And that's right now, because the bottom girder, that is probably exposed to fire, and I want to expose it to fire by a ratio of 30 minutes. And I say, okay, 3 sides of the structure are exposed to fire, and that's enough for me. Serviceability is also relevant for the bottom girder. Of course, that's the most important information for this bottom girder, I think, how much it is deforming. The limit values you can edit here. That's similar to what you can do in RFEM 5. And design supports and deflection, I will also leave the default values. But here you can say if you want to have design supports in it, and also say for the deflection analysis in which direction you want to assign that. I think it's also going to be shown by Gerhard to you later on. Buckling, of course, also for the bottom girder, this is probably relevant, but maybe not. Yeah, well, we could also do it for lateral torsional buckling, but as the load is introduced at the top of the top girder, it's maybe not so relevant in here. And here as well, also for the buckling, we can give it or try to design a little bit more efficient and say in the it's been held in the stronger axis by the stiffening elements, and for the other direction I can choose the whole length of the beam, but is of course 40 meters. So I have this here, service class there as well. All the other elements that I have in here, they are all just stiffening elements. I can actually select them all and say for effective lengths, okay, I'm just verifying buckling, because mainly I'm actually looking for the columns in here, and I will also leave the principal axis by a factor of 1. Design configurations, I want to have ultimate limit state. Of course, serviceability makes absolutely no sense for the other elements. Fire resistance, yeah, of course, for the columns that would make sense, but for all other elements not. And so I'm skipping it for this presentation in here. Press OK, and now my input is actually ready. I can directly design the software, and then for this you go to the columns again, to the timber design, where the former add-on Timber Pro is included. And here you can say, choose what you want to design. Of course, I have my ultimate limit state, serviceability, and also the fire resistance combination, and I want to verify them all. I can check what kind of objects I want to design in this structure, of course, all material configurations and so on. And now when you start the calculation, one thing I wanted to show you when we started, that now with the RFEM 6 we have the option to parallelize the whole combination. So each combination, if you look for FM5, the calculation was done that combination 1 was calculated, combination 2 was calculated, and then after that, and here all 29 combinations are done at the same time. So the speed up process for a lot of combination should be quite good or big regarded it. So you see here, hooray, we have a loading of 100%. Every engineer loves to see this. I think, well, 100% is still red, but I think 100% is a good value to have. That's what we can see here in the overview. And here in the design ratios on members, you see that, well, we have this loading here. And here again, the representatives are a good tool to check the calculations that you did. So when you activate the top girder and say, okay, please show me only the selected objects, I can now take a look at the top girder. And of course, design giving for this, well, that's what we all expected probably, is the stability analysis with lateral torsional buckling according 6.3.3 in the Eurocode 5. And if you go to the detail mask in here, you can look the design check details, and you have all the values written as a very nice equation related also to the equations from the standard, so you can directly vice versa look into the standard and verify all these points. This is probably something you want to have in your printout report. So there we are directly printing it to this. Right in here, I will not show you the whole printout report again, because I only want to show you the parts that are relevant for the timber design. And in this also, I probably do not want to have all points in it, maybe global settings, design situation, materials, actually, yeah, okay, I mean, we can have them. Sections, ultimate limit configurations makes not so much sense. I will show that in the protocol directly. Fire resistance makes sense with also the settings, and in the results I will probably just have the design ratio by the design situation there, and the design ratio by the section, but in the section maybe only have verifications that are over a value of 60%. Everything else to me makes not so much sense. So then I say okay, and on the other screen is now opened that the printout was successfully generated, which is good. Yeah, this, and here you have all the results and the verifications into your structure, and design ratio by section, sorry, is probably something which also is quite interesting. If we maybe go for the representative again, switch that on, you see that also here. So buckling still also for the bottom girder is a problem, and or well, not a problem, but it's design giving in here. And if we look for the columns, you see, well, there's potential to have to save a little bit of wood and money to decrease the size of it. But yeah, you need also to look for the connections. So probably 70% is not that bad to have there. A picture like this, for example, maybe that's not the nicest. Well, why not? If you want to look for the columns, or let's say no, we make it the other way. Hold on. This is representative. So, and then we make selected and related objects. This, and so this is maybe something what is good to have in the printout report, or if we use in the results the static analysis result, maybe also the internal forces for normal force is quite interesting. This design situation is the envelope of all the combinations for ultimate limit state that I have in here. Similar to the result combination what we have had in RFEM 5. So I print that to the protocol and open it directly with this. Yeah, this, well, maybe not the full height. And then I will directly hand over to Gerhard. Height, yeah, let's say, I don't know, we take 50%. Actually, we should have left it this way. Okay, anyway, we print it to there, and yeah. Oh no, oh, sorry, that was my fault. I did not open the protocol, but I printed it directly. Okay, sorry, but I can open it now right here. And I think it's also opening on the other screen. Yeah, that's for sure. Oh no, there it is. Sorry. Okay, then you have the printout report here with the content. You see there's a new fresh style in it. There are a lot of options possible. Long wishes are included in here, unifying PDFs, including the other PDFs, other documents, and so on. That's all possible related to the timber points. Here you have this verification that I mentioned. Here you have the design ratios in it, the configurations for the fire resistance are here, also that you just are exposing it on 3 sides and so on. So that's all included in here. And so I thank you for your attention, and I give the words over to Gerhard. It's your turn, Gerhard. Thank you. Do you grab it your own, or?
Oh, it's okay, Bastian. Wait.
Good. Okay.
All right, perfect. Thank you very much, Bastian. So I have actually 2 examples to show you a few new features in RFEM 6 related to timber design. And the first one is a topic which was missing in RFEM 5. And in RFEM 6 we're proud to offer you this feature. It's about compression design. So when the stresses are perpendicular to the grain, and it was always missing in RFEM 5, and it's an important feature. So we have started to implement this this feature, and it's finished already for general stuff, but in detail or in more complex structures, for example, when a lot of beams come to each other in one node, then it's quite tricky, and we need to find a solution for this to know, okay, where the beam is supported and where the bearing area is, and so on. But I will show you this feature on this floor. So it's a floor with a few beams supported on a downstand beam. So there is no rigid support here along this downstand beam, of course. So we have a semi-rigid support for these beams. Okay, so let's start with the beams. I will show you how to do it. So here on top you will find this tab, Design Supports and Deflection. This tab controls the design supports and also the deflection checks. So we know about Timber Pro, for example, now from 5. There you had to manually define this reference length for the deflection check. And this is done here in this right column. So let's start with the design supports. So of course, first you can think about why is it here on why is it related to a member and not to a support? Yeah, of course, everyone or a lot of people maybe expect that this compression design is related to supports, but of course we have situations where a member end is not supported on a support, but it's supported but on another beam, for example, and therefore it's a property of the member and not of the support. Okay, so we have member start, member end, or member set start, member set end, and here we can define this support. So we create new, and here we will find the settings for timber. So we have, of course, in contact area, which we need to define. So we say it's a direct support, and the support length, for example, in this case, it's 60 millimeters. It's supported on the positive side, so on the plus C axis. It's an edge support and not an inner support. And this KC 90 factor, which it's mentioned in the Eurocode, of course, needs to be entered here. So we use 1.5 for C24 in this example. So let's name it directly by C24 and 60 millimeter. Then on the right side, we create another one. So it's C24-2 and the beam is 180 millimeter. So I will switch this to 180 millimeters and to 1.52. Okay, then the downspan beam, it's a glue lamp beam. It's supported by 140 millimeters. I just rename it to get a better overview afterwards, because these design supports can be assigned to many members afterwards, and that's why I recommend to give them a clear name. 140 millimeters, and in this case we have a factor for glue lamp of 1.75. And of course the beams are supported on top side, therefore we need another one. In this case it's 180 millimeters, and it's on the minus C axis. It's an inner support, and factor is 1.752. Okay, so I assign the support number 1 on the left side of the beams and support number 2 on the right side of the beams. So when you watch this, you see, of course, the edge is missing because we are always relating to the statical axis. In case if you really want to have it, I can show you afterwards by members how to extend this graphically if needed. To be honest, I don't need it, but maybe for some graphical output you can extend it to the end of this design support. Okay, so that's it actually. The deflection check should be in C direction and to the deformed segment ends. So we consider also the deformation of this downstand beam here. And that's it actually for the beams. All right, and now let's go to the downstand beam here, to the glue lamp beam. We go here to this tab again, design supports and deflection. So here you see on the left side, I have this support number 3 with 140 millimeters, and let's go back to this topic to extend the member. So here on the main tab, there is a new option called end modifications, and for these end modifications you can extend here these members graphically only. So it has no influence on the stiffness, on loads and so on. It's just graphically. So this is possible. I will switch it off. I don't need it. Okay. Now let's check this one. We have these intermediate nodes, and of course the load comes from top. So we need, of course, check the support pressure also from top side. So I will assign number 4 for the top. And I hit the F8 button to overtake the column or the cell from above. So that's it. We check C direction again, and as you can see here, we have a lot of segments now because of this. That means the deflection check would now check the deformation in between these nodes. Of course, this is not expected, or this is not the wished behavior, of course. I want to check from node 19 to 20. In this case, just go back to this design support and deactivate this option, consider support in deflection design. When you do this, you will realize, okay, we get one segment again. So in case you have no real support, for example, you have an indirect support, some dovetails connection or some other steel connection and so on, you can simply leave it empty here, or you can simply switch to you can deactivate this option here, direct support to, and then there is no compression design check. So you see, when I deactivate it, all these informations are not necessary. All right, so that's it so far. And then let's go to the results. All right, so we see a ratio here of, close to 100%. There are a few warning messages because I have not assigned any effective lengths, but I don't care of it. Stability is not controlling here. I just check here my stuff per member representatives, and I go to this tab here. Then we see the results of the beams on top and of the glulam beam. You see here there are a lot of SLS design checks, so I'm not interested in all of this, and therefore I say, please show me only the governing serviceability check, and then it reduces all the lines to 4. So we have the check for support pressure, for the shear, bending, and serviceability, and this reduces everything a lot. Okay, so let's maybe check one of them, compression perpendicular to the grain check. So what's happening? Of course, we get our support forces. It's 10.5 kilonewton. Yeah, we calculate this effective area. Of course, in this case, we have 60 millimeters. And of course, we can add this 30 millimeters because of this effect where the grains hook in. And of course, if the member is not really 30 millimeters long, then this is checked also. And in this case, it's 60 plus 30 millimeters equals 90 millimeter, and the width of the beam is 120 millimeter. And we get this effective area here. And the KC90 factor is considered. Actually, it's not a big deal. But the problem was always in RFEM 5 that we had no support. We had no support with, and that was the reason why it was always missing. Okay, so this was this part, and also let's check maybe only the serviceability. And we see the ratio is affine to the deformation, and that's actually what I expect. Okay, so far to this feature, and then let's go to the another one. Seems it was the wrong one now, but it does not matter. I can just go back to the state where I want to start. I delete this and this. Okay. And I will remove all effective lengths, and then we can directly start. All right. Okay. So what do we have here? We have just a simple one-span beam, and it's supported on both sides. We have a load on top, and of course, let's check the length. The length is 18 meters, and the height is, or the cross section is 14 centimeters by 160 centimeters. And of course, because of this situation, the beam is forced to buckle out of the plane because of lateral torsional buckling, and this of course we need to check. I have run the analysis again already, and you see here this error message again: no effective lengths are assigned. The stability design could not be performed. This behavior was changed in RFEM 6 because in RFEM 5 there was always this default effective lengths with a factor of 1.0 multiplied by the member or member set lengths. And in this case, yeah, there was always the problem that a lot of users didn't design or didn't assign any factor or the correct factor. And now, yeah, that's always this message when there's no effective lengths, then you get this warning message, okay, you forgot to assign any effective lengths. That's the reason why we get only shear and bending design and no stability design. Okay, then let's define an effective length for this one span beam. So we can deactivate flexural buckling since I have no normal force in the beam. And let's go to this factor here on the bottom. So this is our our factor where we have to modify our effective lengths. And according to Eurocode 5, yeah, the factor is for this parabolic moment distribution is 0.9. There is an more exact approach in the German annex, and the factor here is 0.885 because I show you this factor now and not the 0.9 because the result is more close to the eigenvalue result what I show you afterwards. Okay, so let's do this. Click OK, and you see already directly that this design support or this supports for the effective length is also considered here in the main model. You can activate it or you can deactivate it. It depends on you. Okay, let's run the analysis. And we see we get a ratio, compared to the cross-section check from 15% to nearly 70%. So what we can see the critical stress, which is determined by the effective length. So it was 0.885 multiplied by this 18 meter equals 15.93 meters, and we get this critical stress here. So and when we divide this critical stress 5.347 divided by our current stress, it's 1.776, we get a critical or a load factor actually of 3.01. So maybe we can remember this factor 301. And yeah, this is the typical solution what you used in RFEM 5 or by hand calculation. But the question is always what happens in case of more complex structures, of more complex supports, maybe supports, intermediate supports, supports on top flange, bottom flange, and so on. Curved beams, tapered beams, and so on. I will show you our second solution for this issue. Oops, sorry. So I will create a copy. And for the second one, I will use our eigenvalue solver. This eigenvalue solver was already part of the EC3 add-on module in RFEM 5 and is also, of course, available in RFEM 6 for steel constructions and now available also for timber constructions. So in this case, I will switch to the eigenvalue method. And in this tab or in this tab here, I have to define the supports. So the effective length factors are not important for now since I use the eigenvalue method. So here you can see the preview, how the beam is supported. And in this case, the default setting is already correct. We have a fork support on both sides, so fixed in Y and about X direction, and that's actually all what I need. So I just hit the button OK, that's it, and click OK, and now let's compare both results. I forgot one thing to mention. And it's about the load position. Okay, so the load position can be defined here in the ULS config of a member or of the timber design. So I set it to shear center to compare the results and to get a better, to get the same values as in both methods. That's why I set it to shear point, because the other solution, when I would keep the downwards option here, the results vary a bit more. So that's why I've set to shear point, but we will switch it later. Okay, so let's compare the results. The ratio with the eigenvalue is 68.3 and 69.2. So the results are actually the same. So let's go to the equivalent member design with an analytical way to determine the stress. So here the critical load factor was 301, and when we switch to member number 2, our eigenvalue solver gives us this factor of 305, which is perfect actually, or which fits perfectly with this analytical solution. And that's why, of course, the ratios are the same in both cases. So our eigenvalue solver is fed by the stiffness and so on as support conditions, and the result is this critical load factor. And when we multiply our bending moment with the critical load factor, of course, we get our critical moment or divide by the elastic section modulus, we get our critical stress, of course. Okay, so this is one example. We can extend it to show you actually the advantages of it. I will divide these members here. Okay, it seems my shortcuts were deleted while I installed the new version, but that's actually not too bad because I can show you another feature in RFEM 6, a new one. All commands here for the toolbars can be assigned to a shortcut. So in this case, I go to Tools and I say here, divide the member using an intermediate nodes. And I assign a shortcut Control T, for example, and then I set it. I select both members, Control T, and this dialog directly pops up. 2 intermediate nodes, and I don't want to divide the member. I just want to have the nodes on the member. Okay. So let's switch this. So what I want to do is I want to support actually the beam in the 3rd points. So I will do this by defining a new effective length with analytical solution. And with analytical solution, we assume the bending moment is parabolic, but in between these 2 nodes, the distribution is nearly constant. And when it's constant, then the factor is 1.0 according to Eurocode tables. It's an assumption, but it's actually a good assumption. It can be used, and it's common to use it in practice. Okay, but of course, when we switch over to absolute values, it's still considering the 18 meters and not the 6 meters. And we can deal with this by adding intermediate nodes, and we have these 2 intermediate nodes. So I just hit this beam. Oh, sorry, that was the wrong one, I guess. Yes, select member, and then we get these 2 intermediate nodes. And the big advantage now in RFEM 5, when you had 100 members, you had to define the effective length for 100 members. And here I can assign an effective length to all members what I have selected. So this is directly a property which can be controlled by these members, and it's a big advantage. So in this case, I say here there is a fixed support in Y direction, so out of plane, and that's it actually. And here I get my 6 meters. Okay. And you see directly this supports. And we do the same for the eigenvalue method. Okay, in Y direction you can activate the default or the preview, and then you see directly where the supports are. Okay, so that's all for now. Just click OK and run the analysis again, and then we can check the results. Of course, the ratio needs to be or must be smaller now than the ratio from the left side. Okay, so yeah, the ratio goes down to 26 by the analytical solution, and the eigenvalue method here. Yeah, the difference is a bit more now compared to the left side, of course, because this assumption that there's a constant moment distribution is of course not completely true, because it's not really constant. Yeah, and that's of course there's a difference. And the big advantage with this eigenvalue solver, you see directly if your supports are correct, because we can show or display this mode shape. Yeah, here of course we have a big sinus wave because we have no lateral restraints, and here on this side you see, yeah, it considers the nodes or the support. And yeah, we can go a bit farther here. For example, we have also the possibility to assign this support at the upper side of the flanges. Okay, so when we click OK, we will directly see it's also moved in the graphics and also in RFEM, so we can directly control actually where the supports are located. Okay, so we had 22 or 23 of ratio here, and of course when the beam is supported on top side, the ratio should go lower. Maybe not much, but at least a bit. Okay, yeah, it goes down to 20%. Okay, let's double check again. And you can see here, yeah, it's perfect support top side, but the bottom side, of course, is able to move out of the plane. Okay, so this is actually all from my side. I have showed you a few, nice features, I guess, in RFEM 6, and I'm, happy to present you all this stuff. And I want to say thank you to you all, and I will give back to Andreas now. Bye.
Okay, thank you, Gerhard, for showing this these additional features. Before I close the webinar, I would like to show you where you can find the recording of the webinar the next days. Just a moment. On dlubal.com, you can find here under news and events the webinars. And this is today's webinar. And you will find the recording here the next days. And when you scroll down, you can find the models here. Okay, then we can close the webinar. I show my webcam again. Thank you for your attention. Thanks to my both colleagues for the nice presentations. Bastian shows his webcam as well. Thank you. Okay, yeah, maybe we see or hear each other in another webinar. That would be very nice. I wish you a nice rest of the day. Yeah, bye-bye.